this problem, we're going to take a look at utilizing a semi-batch reactor system and solving an example problem for a particular semi-batch setup. It's actually a very common one used industrially. And then it's useful to explain exactly how the reactor is set up here, since my artwork's not the best. But what we have is a reactor in which we have a mixed phase reaction between gas phase hydrogen and liquid phase component A, which is an unsaturated compound. We then make a product P. It's also a liquid from this hydrogenation. The way that the reaction is set up for this mixed phase reaction is that you have an impeller that stirs the liquid pretty vigorously to allow gas bubbles to become entrained in the liquid, right, so that you can actually have contact between hydrogen and this A component, and most likely a catalyst. And the way this is set up is that there's a hydrogen source in the laboratory in which this is being conducted, right, in which is basically just a hydrogen bottle, a hydrogen cylinder. And on that hydrogen cylinder is a device that allows us to control the delivery pressure of the hydrogen to our reactor. And so what we have is essentially a constant pressure that we supply to the reactor of 3 bar. And as much hydrogen as needs to maintain that pressure of 3 bar will flow out of the hydrogen cylinder and into the reactor. Okay, and so that means the pressure inside the reactor is always 3 bars of hydrogen, since the vapor pressure of the liquid in this case is negligible. All right, we're given some other information about the conditions, so this temperature actually ends up being irrelevant in the way the problem stated. The conversion to be achieved is 80%. We start with a set number of moles of A, of our reactant, of 150, and again we'll feed as much of the hydrogen as we need to consume that to a conversion of 80%. The reaction rate expression is given here. It has maybe a little bit of an unusual form. It's based on the liquid phase concentration of A and the partial pressure of hydrogen, which is essentially the total pressure of the system. And it's really defined for the volume of the liquid rather than the volume of the reactor, which is sort of a fine point, since the reactor would probably be mostly full of liquid anyway. Right, but this is usually the per volume in this rate term is usually specified as being per volume of liquid. The K has been determined experimentally to be the value shown here, and has a little bit of unusual units with the per bar here because of the sort of unusual appearance of the rate law here. Okay, we're asked to solve for 2 things. First is the amount of time it's going to take to achieve 80% conversion, and second is how will the hydrogen flow rate out of the cylinder and into the reactor vary with time. All right, so we'll want to derive an equation for that and plot it up. But first is just we need to do a calculation of the semi-batch time. And this is a semi-batch reactor system because hydrogen does cross the boundaries during time, and so we'll want to take that into account in our material balances. All right, so the first thing we'll do for part A is to write the material balance on component A. dNA dt is equal to the rate with which A is consumed, kCa pH2, times the volume of the reactor. We will assume that the volume of the liquid stays constant, which for these hydrogenation type reactions is a very good assumption. All right, so dCa dt is equal to then negative kCa pH2. And we will separate out our variables, so we'll pull the Ca over to one side, and we'll pull the dt over to the other side. Okay, we will integrate this expression, which of course has a really familiar form, from Ca naught to Ca. And then this expression over here, what makes this actually easy to solve, easier in the semi-batch case than the batch case in fact, is that the pressure of hydrogen is a constant with respect to time. K is also a constant with respect to time, so we can pull those out of the integral and integrate from 0 to t. And over here we just have negative K times pH2 times T, which is what we're solving for. All right, over here on this side of the equation, we can simply take this integral, and of course it's equal to ln of Ca over Ca naught. And if we have an 80% conversion at a constant volume of our reacting fluid, then this goes to a value of 0.2. final concentration of 20% of the initial concentration if we have 80% conversion. All right, so we need to take just the log of 0.2 on the left-hand side. On the right-hand side, we have the value for K in the given information. It's 0.0074. We have the value for pH 2. It's 3 bar in the reactor. And so then we can just solve for the time. And the batch time that's required, I get to be about 72 minutes. Okay, so that's part A. And we see that really the nature of this semi-batch problem made this problem easier because the concentration of one of the reactants was constant with time. All right, similar to when we were operating in excess, but here we aren't necessarily operating in excess. It's just that we're constantly supplying new hydrogen in this semi-batch mode to keep the level constant. And that's very easily achieved with simple reactor setups. All right, now let's go to part B, where we want to do a balance on hydrogen to determine how much hydrogen is consumed with respect to time. All right, so if we do a balance on hydrogen, we can write that the change of hydrogen with respect to time in the batch reactor system is equal to negative K Ca pH2 times the volume, just like for A, because B is consumed, or I'm sorry, I should be consistent and call B. B is actually hydrogen. So hydrogen is consumed at the same rate as the reactant. It's a one-to-one stoichiometry. And so we have the same rate of consumption here. And then hydrogen, unlike A, also enters the system. And that's what we actually want to solve for. So we want to solve for the flow rate of hydrogen coming into our system. Okay, so this is a typical semi-batch type balance. But unlike some of the problems that we've seen in the textbook, it actually gets a little bit simpler because there's no net accumulation of hydrogen. The pressure is 3 bar at all times. All right, so there's no, and since the temperature is also constant and the volume of the reactor is constant, that means the moles of hydrogen inside the reactor are constant. All right, so this term goes to 0. All right, and that's going to end up making our life a lot easier. So we can just set this expression equal to 0 and solve directly for FH2, that is equal to K times the concentration of A times pH2 times the volume. Okay, now we know that we want to determine this as a function of time, and it's not immediately apparent over here that time is involved here, but remember that the concentration of A actually is going to decrease with time because we're reacting away A. We're not adding any of that to the reactor. Okay, so we've already solved for that relationship, and it's on the previous page. The concentration of A was inside a logarithm, so we're going to change it into the exponential form that will look very familiar. So what we'll get is a K pH2 volume, then times Ca naught, the exponential of negative K pH2 T. Okay, and this term is what we got from our mole balance on A. So this is, if we express concentration of A in terms of time, if you look back earlier in the problem, then this is what we'll get. We'll get the Ca naught times this exponential term. All right, we can make a further simplification here. All right, that V times Ca naught is equal to Na naught. So the volume times the moles per volume is equal to the moles of component A. All right, and we know this value. It's given in the problem statement as being 150 moles. We know pH2, it's 3 bar. We've been given K, it's the 0.0074 value. All right, K shows up again, 3 bar. And so now we have all of the constants we need, and as a function of time, we can determine the value of the flow rate of hydrogen. And so I've just plotted up this expression very simply in Excel. All right, so here we see the flow rate of hydrogen in moles per minute entering the reactor. That it starts out at a little bit below 2.5 and then decays exponentially from there as we expect. All right, so it decays in a first order type process as well because the concentration of hydrogen in the reactor is constant, and it's an effectively first order process. All right, and we see that at about 72 minutes, so the batch time that we need, the flow rate of hydrogen has decreased to approximately 20% of its initial value, which is what we expect for 80% conversion, right? Since at that point, 80% of the A has been consumed, and so therefore 80% of the hydrogen should have been consumed. And so we should be flowing in hydrogen at a rate that's slower than it was before. That's 20% of what it was before. Okay, so we can see that in many of the cases that we've looked at for semi-batch reactors and that are in the textbook involve more difficult solutions of mathematical expressions. But in some cases, semi-batch reactors are both easier to analyze in terms of the equations. And this is actually a system that in some ways is easier to set up than a bomb reactor, that you can very simple to get a hydrogen cylinder with a pressure control device to keep the delivery pressure constant at a set value. And so it's both a simple setup and a simple analysis.